In this lab, I analyzed the motion of a spring mass system whose position was changing in both the x and y directions. The main purpose of this lab was to use the energy principle in order to predict and analyze the motion of a spring moving in more than one direction. To do this, I made a model that would update the mass's position based on the different forces acting on the mass on the spring and assuming frictional forces to be negligible. I found that the energy principle did give close to perfect results for predicting the spring's motion, though there was some error because of not accounting for air resistance in the model. Therefore, the change in energy in this system should be equal to zero. The main physics principles needed in order to analyze the spring's motion include Newton's second law, which states that the final velocity is equal to the initial velocity plus the F net over the mass times delta t. The F net in this case was equal to the force of gravity on the mass and the force from the spring on the mass. We will also need to make use of the energy principle, which states that the change in energy is equal to the work done by the surroundings. Choosing the Earth, mass, and spring as our system, we know that the work done by the surrounding is equal to zero, and therefore the change in energy is equal to zero. We will also use Hooke's law, which will be explained later. Now let's use these in a computational model. From the tracker data, I found the initial position vector and used the first 2 points in tracker in order to find the initial velocity of the spring. In order to find the stiffness constant of the spring, I had to use the period of the spring, which is equal to the number of oscillations the spring makes over a certain amount of time. I then had to initialize the relaxed length of the spring using Hooke's law. Hooke's law states that the force of a spring is equal to the negative value of the stiffness of the spring times the stretch of the spring. I could then initialize S to be equal to L minus LO. I also had to initialize the kinetic, gravitational potential, and string potential energy times the stretch squared. Within the while loop, I initialized the initial energies that were defined before. I then went through and found the force of gravity was equal to negative of the ball's mass times gravity, and the force of the spring, which was found using Hooke's laws. The net force was then equal to the force of the spring plus the force of gravity. I then used this net force in Newton's second law to update the velocity of the ball. With this updated velocity, I could find the updated position of the mass on the spring. I then had to update S, the change in position of the spring. In order to find the changes in energies, I updated the energies using the values I just found and then finding the difference between the final and initial energies. Here you can see that the final kinetic energy is equal to 1/2 times the ball's mass times the velocity squared, and the change in kinetic energy is equal to the final kinetic energy minus the initial kinetic energy. And there's the same pattern for the rest of the energies. As you can see in the upper graph, the total change in energy, represented by the yellow line, looks to be about zero, meaning the principle of energy was successful in this model. You can also see how the gravitational potential, the green line, and the spring potential, the red line, were somewhat canceling each other out to get the value of the opposite of whatever the kinetic energy was equal to, the blue line, making the total change in energy equal to about zero. In the bottom graph, you can see that in both the x and y positions, my model did fit the tracker observations of the position quite well. For the x position, the blue line represents the model position in x, and the red line represents tracker's position in x. For the y positions, the yellow represents the tracker's position in y, and the green represents my model's position in y. There are a few inconsistencies, which can be due to not accounting for air resistance in the model or human errors in tracker. Let's take a closer look at the total change in energy to see if it is truly zero. Clearly, the total change in energy oscillates on an incredibly small interval. So, although it is not exactly zero, it is very close. These differences could be due to not accounting for any work done by surrounding forces, such as friction and air resistance. Moreover, we can estimate the periods in both the x and y directions from the observations in tracker. the period t is equal to the amount of oscillations over the change in time. We can see that the periods of both x and y are not the same, making the spring move in a seemingly scattered and complicated motion. Also, the period in the x direction is not fully constant, which could affect the value of k. Since it is not constant, the value of the period would be changing over time, meaning that the stiffness constant would also be changing over time. The period in x is almost basically constant, however, so it shouldn't have affected it much for this lab. In all, the energy principle proved to be effective and true for this lab. This lab helped us understand how we can use the energy principle in the real world and see that it is indeed effective in most applications.